Hello, everybody. My name is Angelos Stavrou, and today I'm going to be talking about IoT sensors for agriculture, opportunities and security implications. Before we start, I'm going to talk a little bit about who I am. I have a Columbia PhD from 2007, and now I'm a full professor at Virginia Tech, the Electrical and Computer Engineering Department. At the same time, I'm a founder of a company on mobile security space called Kryptowire, that's very successful. And my research has been in cybersecurity of large systems, IoT and wireless, primarily 5G and 6G. But let's start talking. Why smart agriculture? As you can see, smart agriculture has become a very, very vibrant field with annual rate of increase of 10.1%, projected to go to 2.8 billion in 2026. In fact, Asia Pacific has been on the forefront of smart agriculture because of population, but also the bloom of technology. At the same time, a lot of product launches and developments have actually been announced. And today I'm going to be talking more about why smart agriculture can benefit for some of the IoT technology that I've been working on. So if we take a look at this global smart agriculture market, you will see that there is a lot of different areas that has been fruitful. For example, you can see that the yield monitoring, field mapping, crop scouting, weather tracking and forecasting, farm labor management, inventory management, and irrigation management. Today, we will be talking more about how all of these precision farming applications are affected by IoT advances and what are the barriers to allow us to grow in this field. The global market size in 2021 was 14.4 billion, and it's growing. So how does IoT come into play with agriculture? There are a lot of sensors. In this case, we consider sensors like humidity, soil management. A farmer basically is connecting his fields, creating a situation where there are a lot of distributed sensors providing real-time monitoring. And the data are coming from servers and going to servers. The important part is that, for example, you can have things like an IoT tractor or drones, all of them managed by the same system. One of the interesting problems that we've seen in the past is that there has been a disconnect between what the IoT devices can offer and how they can be managed in a situation with agriculture in a manner that's secure and cannot be used by others. I will elaborate more on the next slides. So what type of sensors have you seen in agriculture? Many of the sensors that we have been discussing are water monitoring, soil and moisture monitoring, also temperature and humidity sensors, and they have a lot of the different applications, as you can see here, that we have broken down. Part of the operations that we see are, for example, irrigation, fertilization, soil analysis, and field condition. Now, as we are starting to understand better why IoT are important element of the smart agriculture, we start realizing that there are also potential for disruptions as we deploy those. And some of the disruptions come directly from cybersecurity challenges. Here in this slide, I've listed some of the OWASP cybersecurity specifically for IoT devices. And you can see here inefficient authentication authorization, including weak passwords, lack of encryption. And in general, we see a lot of problems with how the devices are connected with each other. Part of the problems that we see stem from the fact that IoT devices, when they come from the manufacturer, might not necessarily have compatible interfaces to be put together, especially when it comes to security, leading to people, especially people who are not experts in the space of cybersecurity, to disable the authorization and authentication schemes in order to collect the data. So today, I'm going to be talking about a system that we have devised to prevent some of these threats that we see here on red from actually taking place. So one of the most interesting questions that I get when I talk about the space is, we have solved the problem on other devices, right? We already know how to connect our laptops to the cloud and have cryptography take care of everything. One of the things that most of the people that I discuss forget and they do not understand clearly is that some of these devices that we are talking about that are actually deployed in agriculture are very, very small devices, and they do not have the storage and CPU to support the cryptographic operations that we would like. For example, here in this picture, you see devices such as Arduinos and Intel Galileo. All of them are actually requiring 12 seconds even to, for example, encrypt something small. You can imagine that this basically not only create a problem in terms of how many operations we can do per second, but also the dry battery, and they're not efficient for the small sensors that we have deployed. And deploying more expensive sensors means more expensive requirements for agriculture, smart agriculture, and in many, many cases, that means that basically we cannot deploy them because they just are not cost efficient. So many of the traditional crypto make the devices and expensive. So most people opt out for smaller and less powerful devices, but at the same time, that means that they cannot operate on the traditional cryptographic scenario. So one of the ideas that we have been working with my group is, can we use blockchain-inspired protocols? In fact, can we replace traditional cryptography with blockchain? Can we, for example, replace authentication and trust among untrusted parties, meaning that can we deploy sensors that are actually deployed not only in one crop, but maybe across crops? So for imagine you have multiple agricultural parcels and they're managed by different people, but they still want to be able to exchange information about moisture and weather, so they can create a group of trusted parties. And how can we exchange information, only the information we want, and at the same time create a sustainable and potentially auditable mechanism? For example, the government might come and check how the crops are doing, but they can actually do it without interfering with the sensors. So some of the strengths that we have seen in using blockchain-inspired protocols for IoT in agriculture is we can actually do a fully decentralized network with a distributed resilience and control, meaning if some of the sensors go offline, we can still recover information. It's all open source, which means low cost, and the security and modern cryptography is allowed, and we will see how we can replace some of the operations with lightweight operations. You can actually control, can have an open participation, and we can do also things like smart contracts and dynamic and fluid operations. Smart contracts, for example, can be something that allows us to exchange information for a fee to other parties. We have a lot of desirable properties for blockchain. For example, the distributed protocol is a distributed protocol with verifiable transaction history. It has dynamic membership and supports what we call multi-party signatures. However, if we take the traditional blockchain and we try to apply it directly to IoT devices, we find out that there are a lot of issues. For example, one of the biggest problems is the requirement for proof of work. Bitcoin, for example, is one of these protocols which require proof of work to participate in the blockchain. However, such participation with proof of work is energy consuming. It's something that for certain is not appropriate for IoT devices and cannot be applied directly. Also, we have the requirement, what we call of PKI, which stands for public key encryption or public key infrastructure, which is computationally expensive. As we saw in the slide, couple of slides before, RSA operations are prohibitively expensive for small IoT devices and sensors, and we want to be able to use those to collect the data. How can we do that if they're too expensive and energy inefficient? We'll see in the next slides how we can actually change that. The size of the ledger. Size of the ledger is an issue for small devices. In blockchain, the size of a ledger is the size of basically the per round operations that need to be performed, and we actually will show that this ledger is pretty small. And also part of the undesirable properties is the anonymous and unverifiable join and leave operations, which is desirable for a blockchain application, but undesirable for an agricultural system where each parcel and each IoT group needs to have some sort of authentication and belong to a farmer. Maybe farmers can have deals between them to exchange data, but that cannot be done having an anonymous, unverifiable operations while the IoT devices join and leave. So what can we do about it? We can actually eliminate the undesirable properties. So the requirement for proof of work can be changed and modified to require proof of earlier participation using history. We will see that we use what we call hash chains to achieve that. Instead of required public key infrastructure, we replace the public key infrastructure requirement, which is actually the most stringent one, with hash-based signatures or other Merkle tree schemes. We will talk about the Lamport scheme in a second. The size of the ledger can be an issue for small devices. We basically prune and compress the ledger. We maintain only device-relevant transaction ledger when the device is too resource constrained. The idea here is that we reduce the size of the operations to the bare minimum for small devices, and we use these operations smartly to convey the proper information instead of serving a lot of information, logging information. So instead of anonymous, unverifiable join and leave operations, we replace those with crypt signatures using pre-shared group keys. So what is our approach? Our approach is called Black Box IoT. There is a relevant publication you can see on the bottom right. Here I'm going to give you a brief taste of what this application is about. The paper has the full version of our approach with a lot more measurements and details. So the complete blockchain, it's a complete blockchain system, the Black Box IoT. It's a complete blockchain-based system for industrial level IoT sensors with authentication and group membership. It utilizes a modified approach of the Hyperledger Fabric framework, which is very well known, and it's tailored for extremely constrained devices, which we call class 0 devices, devices basically that have very, very little memory and CPU. And we can actually have some prototype results that I will present today, showing that actually we can use those for small IoT devices, sensor-based IoT devices. Those devices, again, they're called class 0. And also in our approach, we include what we call a comprehensive security threat model, meaning that attacks against the data, the communications of the devices, and also the way that the devices are basically set up to be in a group. And what bad guys can potentially do is actually examined thoroughly in the paper. One of the key components that we have introduced on this paper is called the novel hash-based signature scheme. And that I'm going to talk about immediately next. Back in 1981, Lamport created what we called one-time hash passwords. But the idea of this is that the client generates iteratively a list of hash values in reverse order of index. For example, hash of an initial element, then becomes hash of that initial element, and so on. And basically, if you see Z0, which is the hash of Z1, which is the hash of Z2, becomes the public key. Why we can actually do that is because we can actually reveal the keys in opposite order starting from Z1. So for example, we can actually reveal Z1, and then from there, we can show that we know basically the next value. So the idea here is we can actually go on and basically reveal. So the verification of ZI is starting from ZI. We verify if Z0 is indeed the ith hash, and the keys can be used only once. So the idea here is that if I give you the ith element to prove to you how I went there, I'm giving you the I-1 element. And then I can do that for I-10 and so on. So let's see how that looks like in practice. We set the counter to 0, and then we read the counter, and we can use basically pebbles, meaning that we can actually skip some of the hashing because we have forward put passwords and positions to be faster, and then we verify if they have correct basically hashing. The signing cost for the entire operation is just O of log n, where n is the number of the size of the chain, and the verification cost is basically O1, and there is no need for synchronization. In previous work, there was need for synchronization, and it was too expensive for class 0 devices, and of course not applicable. But how much better can actually black box IoT do? So here you see on the top is electrical DSA can only do 7 operations on a class 0 device, while for the same amount of time, black box IoT can perform almost 3,600 operations, which is basically, this is the number of devices that we did on a 20 milliwatt battery, which is very, very small. And you can see here in comparison with ECDSA verification and unreliable connections. And then here's on the x-axis, you see the outage depth, which is the hash chain elements, and the time to verify. For small elements, you can see we do much better, basically, in terms of verifications. It takes many, almost 2,300 verifications to reach the cost of the ECDSA. But what about security? Now, Professor Yatu showed us the black box IoT. How about talking about how much more security is? The security of the signature scheme and the security of the blockchain consensus properties allow us to even defend against man-in-the-middle attack scenarios, because we can actually compare the data of the blockchain level from different aggregations in the same group, preventing someone from being able to disrupt our ability to secure the data. There's proactive consistency check. Someone cannot create attacks where poisonous data gets into our stream, and we can raise alarm if we detect such an attempt. An attacker might manage to launch an attack, man-in-the-middle attack between a sensor and an aggregator, but attacking, for example, everyone in the device group simultaneously is much harder and cannot be easily performed. It requires a very, very strong adversary that will go and attack all the sensors, for example, in an agricultural approach at the same time. And that is very, very hard. In summary, IoT devices are an integral part of smart agriculture. Why? Because they're deployed everywhere. In our approach, when I talked about IoT devices, I also include the devices that are, for example, drones and everything that basically has depends on very little CPU and processing power, or has energy requirements. For example, the ability to have a battery. The security and privacy needs to be protected. Why? Because an adversary might actually try to block and disrupt the crop from an information, or poison the information in a crop. Moreover, when you start thinking about collaborating between, agricultural farms, you want to be able to use something like blockchain, which prevents unnecessary leakage of information and ensures through smart contracts potential collaboration. A blockchain approach for authenticating the industrial IoT sensors, which is tailored, mostly constrained for class 0 devices, is important, because what we have so far in terms of blockchain secures data on servers. And that is something that is desirable only for servers, but we also want to extend it for sensors and IoT devices. Also, another important feature of our approach is that the sensor setup phase can actually happen during sensor manufacturing, which means that the manufacturers can label, for example, with a QR code, the IoT sensors, and then as the person who basically deploys them can actually use that QR code to synchronize the sensors and let them run. In our approach, the sensors can run for 20, 30 years without having to rechange the key material. In our approach, which I didn't go too deeply here, but there's in the paper, there is a comprehensive threat model. And in our work, we show practical results for class 0 devices using a prototype, which means that the code that I mentioned is actually available for anybody to use. and we can actually demonstrate it for IoT devices that are fairly constrained. I would like to thank you. If you have any questions, please feel free to email me. My contact information are available online, and I would be happy to answer any questions via mail if you have any. Thank you very much.